Oh, Kim, you got my biscuits. Now tell me, do they taste the same or different to the Tesco biscuits? Because I got them in Lidl. You didn't try them yet? Oh, I see. You're saving them for an emergency. They're only $1.79 in Lidl. Bargain. Bargain. Right. Okay, electrical potential. You can write that down. Matt, your headphones, do they have noise cancelling? They do. Active noise cancelling. Like it cancels out the sound. Okay, you wrote that down? Continue? Okay, alright. Yeah? Sifa? Yeah? Okay. Couple of formulas to do, okay? So, we know from mechanics, when a particle is above the ground, it has potential energy because of forces acting on it, which could cause an acceleration, which could increase the speed, and therefore kinetic energy. The kinetic energy must have come from somewhere. It came from the potential energy at the start. This is the idea that we have in mechanics. When a charged particle is between two parallel plates, there's a force, just like gravity, attracting the particle to the plates. Therefore, it has some potential energy, it should say. So look, I'll give you the picture to explain what's going on here, okay? So this is what we looked at in mechanics. Oops, sorry. Here's the ground. Here's a particle. It has a mass m, and let's say its distance here is d, and there's a force acting down here, and that force is equal to mg. And what did we say the potential energy was equal to? mg d in this case. Okay, so far? It's just for a view of mechanics. Now let's look at what the situation is in fields. So you have two plates, and let's say you have a positive particle here, and this plate is negative. So what will happen? This one will move down. Okay. What's the force here? Remember the formula. F equals EQ. Yeah? So that would F equal EQ, or I'll just write QE. Okay? And this particle has a charge Q, and there's a distance here, D. Now, can you see that it's actually a similar picture? This one, it's being drawn to the earth. This one, it's being drawn to the negative plate. This one has a force mg, and the m is because it has a mass m. And this one has a force QE, and it's a Q because it has a charge Q. Okay. Where did the G come from? The G is due to gravity. So the G is due to gravity. And where did the E come from? The E is due to the field. Can you see it's really a similar situation. So if we were to try and figure out what the potential energy is by comparing it to the mechanics picture, what would it be? Yep, very good. So this charged particle has a potential energy, and it's equal to QED. Now wait, just before I go on, when I get to the end here, this has kinetic energy. What's the kinetic energy? A half v squared. And we can say that mgd equals a half v squared. So we can do the same thing here. We can say QED equals a half v squared. So we could actually use this formula to calculate how fast the charge hits the plate. like how we can use this formula to calculate how fast the mass hits the ground. Can you see the similarities here? Yeah? So, just before we move on, and I'll let you write this down in just 1 second, let's just look at each part. So here the d is the distance, and here the d is a distance. M is a mass. This is a property of the particle. You know what I mean? A feature of the particle, a property. And here the Q, it's the same thing. What's the E here? That's the electric field strength. So the G has a similar function. It acts like a strength. For example, when you're on the moon, is this G bigger or smaller? Smaller. So it's kind of like a strength. Yeah. Now, think it'd be great if you can copy this picture into your notebook. Try and copy this in. I'm so glad we had next week off. You're probably glad too, right? Just a little bit. So has anybody seen George the last week? No. Should I just stop asking? Should I just, let go and maybe... See about the mosque tomorrow, they're having an open day from 3 o'clock. Most importantly, free food, I heard. So they said they'll take you on a tour. Yeah. I've never been inside the actual mosque part, just the food part, so it'd be interesting to see what it's like. I won't have to convert to get the free food, will I? No, I'm just wondering. Because you know what they say, nothing in life is free. So. I like the guy who runs the cafe, Junaid, the guy who does the food. He seems very friendly.
Which one is he?
He's the... There seems to be 2 people who are serving mostly.
We actually never knew his name, we just...
Ah, yeah. He's the guy who gives you the food. Yeah.
With glasses or not without glasses?
Without glasses.
Oh, yeah.
Yeah. Yeah. He's friendly, isn't he?
Yeah,
he's friendly, yeah. Okay, did you copy this down? Yeah. Continue? Ciao? Yep. So, we have the formula, I think you wrote it down. The potential energy caused by the electric field is given by QEH or QED or whatever letter you want to use. Okay. Now, please just be careful here. Yeah, maybe I should have called it H actually, because I want to maybe distinguish between 2 different letters here. Maybe you should add this. So when I use the letter, just to be clear, okay, usually when I use the letter D, I mean the distance between the plates. And h represents the height of the particle, which often is the same. In the exam, it's not 100% of the time it's the same. However, it's possible that the particle begins here. But that's not very realistic, because how did the particle get there unless somebody pushed it in? You know, so usually it's equal to the, usually we say the h and the d are the same. Okay, but technically it doesn't have to be the same. Now, that means we can simplify our formula. Okay, so we have PE equals QED. But we have a formula here for the E. I don't know if you remember, but the E is V over D. Do you remember that formula we did last time? The E is V over D. So what cancels here? The D. So you actually get this simpler formula. It's charge multiplied by voltage gives us the potential energy as well. Okay, and in fact, this is the more common one you'll need for the exam. I was just saying, and last week, I feel sorry for you because you seem to be sick now for the last few weeks. Are you feeling any better, or are you still sick?
I am slowly dying, man.
Slowly, yeah. It seems like it. Are you taking anything for it?
No,
Nothing?
yeah.
Okay. Right, you got that formula? Yep. Okay, so, next now. Oh, just a little bit of vocabulary. Now, you might know this vocabulary from chemistry. These plates here, they have a name. So if this is the positive plate and this is the negative plate, you actually have names for each one from chemistry. I wonder if you know it, or maybe you don't know it from chemistry. This plate has a name. You call it the something plate and the something plate. Yeah, which is which?
I know it's negative and injector is positive. Or is it?
I think it's the other way around, because I think you use cathode and anode to mean ions, don't you? Like, do you say like cation or something? And what's a cation? Positive one?
Positive.
Yeah, but for the plates, the cathode is the negative plate. Maybe because that's where the cations go. And an anode is the positive plate. You got that vocabulary, Matt? Yeah. Okay. Okay, continue. Yeah, Joe? Yeah, okay. Now remember, well, let's see if you remember. If potential energy is positive, we say the charged particle has potential energy. If it's zero, what do we say? Yeah, but we give it a special name. Remember, we did this in mechanics lesson. Forgot. No? Nobody remembers what we called this? Think back, semester one. No, nice try, but not stationary. No one remembers, Kim? Not?
No height.
Oh, no. No. If the potential energy is zero, we say the particle is free. Seems familiar? And if it's negative, yes, we say it is trapped. Okay, since you forgot that, I think you should write it down again. have class tomorrow at 3 o'clock?
Yep.
Okay. What class have you got?
English.
Which teacher?
Connor.
How would you feel about going to the mosque for a tour and free food instead of English?
That would be nice.
Because Emer keeps asking me to do something with the 2 engineering groups. Maybe I could take you guys and the other guys, we could all go on a tour of the mosque and have free food afterwards. Or you could have English. You wouldn't object if we did this, no? Okay. I'll talk to Connell then and see if he'll allow this. Yeah? Alright, did you write that down? Not yet? Okay. I've never been inside a mosque, and I doubt the Chinese students in the class have been inside one. Have you been inside a mosque, Chow? One time. Oh, very good. Okay. That's one more than me. I've been 0 times. Okay. Continue. Yep. Next now. Oh yeah, I already talked about the distance, so that's fine. Okay, so the conservation of energy. We actually mentioned this a little bit earlier. Remember, you don't have to write this down if you remember. Conservation of energy means that the initial energy equals the final energy. So, you don't have to write this down. I think you all know this already, right? Energy at the start equals the energy at the end. Yeah. Kinetic plus potential equals kinetic plus potential. So we can arrive at this formula, PE equals QV. But I think we mentioned that earlier. Anyways, what to look at now? What unit do we use for Q? It's coulombs. And V is volts. The only problem is, this Q is usually a very small number. Like, take for example the electron. What was it? 10 to the minus 19, was it, for the charge? Yeah. Now, it's so small that we can't use any of our prefixes because what's micro? 10 to the minus 6. Nano? Minus 9, okay? And we're at minus 19. So we actually need to make a new unit to measure really small energy levels. So because the Q is so small, we need a different unit to measure energy. And we have this unit called the electron volt of energy. It's a really, really small unit of energy. I don't know if anybody's heard of this unit. No. What an electron volt is, it's the energy gained when one electron is accelerated by an electric field of potential difference of 1 volt. Now, I'll just pause before you continue writing it down, so I think a picture would be good as well, okay? If you can draw a picture with this. So, if you look here, here's the positive plate, here's the negative plate, and here is 1 electron, and here is 1 volt between the plates. So there's a 1 volt, wrong way, 1 volt power supply here, 1 volt. This electron here, it has potential energy, doesn't it? Because it's about ready to accelerate and get kinetic energy. What did we say the formula was? QV. Now what's the charge for Q, for an electron? What letter do we use, do you remember? It's E. And what do we say the V is here? It's 1 volt. So in this picture here, the amount of energy we had would equal E joules. We call this 1 electron volt of joules of energy, or 1 electron volt of energy. In other words, you can think of it like this. 1 EV equals E joules of energy. So you can see it's a very small unit. It's like 1 electron volt is 10 to the minus 19 joules roughly. Okay, so You can write the definition down, but I'd also want you to draw the picture with the definition to help you remember it, okay? Does anybody here watch any sci-fi shows? Star Trek or The Flash or anything like that? None of you? Ah, come on, you're all engineers. You must watch some sci-fi show, no? Matt?
Not the.
No. Siva? What? Kim? No sci-fi shows. Sci-fi shows on deck?
I used to watch The Flash, but not anymore. So.
Yeah. Yeah. Chow, do you watch any sci-fi shows?
What is that?
Sci-fi like space, aliens,
Ah, yeah.
superheroes.
Interesting.
It's interesting, good.
Yeah.
I'm glad you say this.
Black.
Black Mirror.
Yeah.
Yeah, good. Now the reason I say this is because it's a very common mistake in sci-fi shows. They often measure, to sound cooler, they measure energy in electron volts instead of joules. So instead of saying, oh, it's so many joules, they say, oh, it's so many electron volts. The only problem is the electron volt is really, really small. So they try to make it sound dramatic, you know, there's 500 electron volts. Like, yeah, but that's nothing because it's 500 times 10 to the minus 19 joules. No, I was just noticing it this week again. I was watching a show and they're like, oh, you can't touch the computer. There's 500 giga electron volts. I'm like, yeah, but that's not even 1 joule. You know? Yeah, these are the things I notice when I watch TV. So electron volt is a very, very, very small unit of energy. That's the point here, okay? It measures a very small unit of energy. If you can draw the picture with the definition too, please. Got that picture? Yeah. Okay. Right, I'll just, to get started, a small question for you. Convert 1 electron volt into joules. So we'll do this one together. So 1 electron volt into joules would be 1 times E joules. And how big is an E? 1.602 times 10 to the minus 19 joules. So can you see that 1 electron volt is quite small? Okay, that's easy. I'll give you one to try now. Will I continue?
Yep.
I don't know if you need to write that down if you want to. It's up to you. Continue?
Mm-hmm.
Yeah. So look, here's one I want you to work the other direction. I want you to change 1 joule into electron volts. So it's the other direction. Okay, you got an answer? What did you get, Siva, if you have an answer?
6.24 times 10 to the power 18.
Yeah, it should be a big number. Did you get that as well, Andy?
Yeah.
Great, okay. Did you get that, Joe?
No.
I should write it down here for you. 1 joule equals, so you have to type in then 1 divided by E electron volts. So, I don't know, let me see your calculator, I'll show you. Yeah, that one. Oh, you just need brackets.
Ah.
There you go. Got it. Did you get it, Kim? Yeah, okay. Right, 2 more questions here. So let me do this one with you. 2 plates are separated by 2 centimeters with a potential difference of 500 volts. An electron leaves the negative plate and accelerates to the positive. How fast will it hit the positive plate? So I'll draw the picture. You have 2 plates, a negative, a positive. The distance here, 2 centimeters. And it's 500 volts. And there's an electron here. And it moves down and it hits that plate. And I want to know, how fast is it going? So the potential energy here should equal the kinetic energy here. What's the formula for potential energy, guys? What's it? QV for voltage. And that should equal a half mv squared. Okay. Do we know the Q? Yes or no? Yeah. Do we know the V?
Yes.
And do we know the mass? We do, I gave it to you, mass of an electron. So the speed would be root 2q voltage over mass. That would be the answer. So if you can take out your calculators, this is the charge of an electron and the mass of an electron, which I gave you last week, I think. I think I can get it on my calculator. Meters per second? Whoa. Did you get that too, Siva?
1 to the power minus.
Because Matt made some mistakes last week on the calculator, so shall we check Matt?
Okay.
Yeah, why? Oh dear, why not? Yeah. Right, so that's 2 Q E V over, and then mass is, I think, 3? Yeah, I mean the constant number. Uh-oh. I think you're right, Matt. Congrats. Good job. 1.33 times 10 to the 7, yeah. So that's going pretty fast when it hits the plate. Yeah, continue. Now, let's see, what's next example? An electron enters a field which is at a potential difference of 10 kilovolts. The electron accelerates across the field until it hits 3 protons at rest on the positive plate. The electron binds to the protons and they move off together. How fast did they move off at? So I'll draw the picture here. You have a positive plate and you have a negative plate. And you have the electron, and it comes along here, and then it hits 3 protons. 3 protons. And then the 4 of them, so the 3 protons and the 1 electron, they move off the plate together. Or maybe they don't move off the plate, but they move anyways. Okay. And my question is, or what else do I tell you? This is 10,000 volts. And my question is, how fast do they move? Okay, so this is a bit harder now. So, first things first. Here, the electron has potential energy. And just before it hits the protons here, it has kinetic energy. So, it's the normal story. What do we say? Q V equals a half v squared. Yeah? Same as the last question, right? So, since I still have it on my calculator, let me just go back to my calculator. What is the number I need to change here on my calculator? What number is different in this calculation?
500.
Yeah, what should it be?
10,000.
10,000. Is that okay? Did I just do that? Yeah? That's 5.93 times 10 to the 7. Okay, but now, look. These two collide and they move off together. So what type of problem is this now? Conservation of, yeah, that's it, momentum. So you have m1u1, m2u2 equals momentum here, okay? So you have the mass of the electron times the velocity of the electron times the mass of the protons, mp for proton, times 0. That equals mass of the electron plus the mass of the protons times, and we'll call this speed here x. And I'm looking for x. Okay? So that's gone. And I get x equals ME 5.93 times 10 to the 7 over mass of the electron plus 3 times mass of the proton. So we'll need to type this in. But I just want to show you a little, before you type it in to calculate the exact answer, I want to show you a nice little shortcut here. Can you scroll down a little bit? So look, please note that this is, what I'm about to do is just an approximation, okay? I actually know that the mass of the proton is about 1,000 times bigger than the mass of the electron. It's roughly about 1,000 times bigger. And maybe you know that from chemistry too. So what I can do is I can replace this with mass of the electron plus 3,000 mass of the electron. Now the reason I want to do that is because I can cancel all of these. So I'm just left with roughly 3001, which is about 3000 still. 5.93 over 3001 times 10 to the 10 to the 7. So that's roughly 5.93 over 3 times 10 to the divided by 1004. So that's roughly 2 times 10 to the 4 meters per second, roughly. Okay. Now, of course, in the exam you use your calculator here, but I think my answer will be pretty close to the true answer. So let's find out. Mass of the electron. Mass of the electron plus 3 times mass of the proton. And then on the top, did I get that all right? Yeah, so what did I say? Divided by 10 to the 4, wasn't it? Ah, it wasn't that close. 1.07 and I got 2. Okay. I thought I'd be a little bit closer. or actually, mass of the proton or electron, yeah. I'm just wondering, I thought it was 1,000 times bigger, isn't it? Ah, no, sorry, it's nearly 2,000 times bigger, not 1,000, sorry. So, here, I should have said 2,000. So that here would be 6,000, which makes this one 6,001. Okay. 1. Yeah, so my answer was 1 times 10 to the 4, whereas the true answer is 1.08 times 10 to the 4. So without a calculator, you can get a pretty accurate answer. If you want to write the true answer down, that's it, 1.08. Okay, is that one okay? So good job, Siba, you had the idea of conservation of momentum here. In the exam, it's usually just like the last example, not with the extra piece usually. Okay, continue. Do you know where these are on your calculator, Chow? You press Shift 7, and then number 1, is mass of proton.
Yep.
Number 3 is mass of electron,
Mm-hmm.
and 23 is charge of electron. They're useful. It's useful. Okay, can I close this? Yeah? Let's see where you're at. Yeah, question time. Now, I think what we'll do is I'll let you try these for a few minutes, and then we'll do the tutorial on electric field strength formulas. Okay?